Well, good morning. Bill Ragsdale here, representing the Silicon Valley Fourth Interest Group. Delighted to be doing presentation today. We are going to be discussing vocabularies, and in particular, the vocabularies as they're used in Win32F. We'll see the use and the structure of vocabularies, how they're put together, how they're used, and some of the pitfalls. We'll do a historical view to discuss the introduction of the words only and also. We'll see some support words, how they're used in Fourth. I'll offer a couple of cautions in the use because there can be some pitfalls associated with vocabularies. So the first question is, why do we have vocabularies in Fourth? Well, vocabularies segment words into word sets, of course, named vocabularies. There is a vocabulary named Fourth. In Win32F, it has 2,441 words in it. But there are, as we'll see, a total of 14 vocabularies. Rather than having to remember all those words in 14 vocabularies, we can, at any given time, you only have to concentrate on the words that are in a particular vocabulary. The usual minimum number of vocabularies in a Fourth system would be the word Fourth itself, and then an editor, some way to display and enter text and edit, and generally an assembler so you can do programming and machine code. There could be some additional words such as file system or usage of mass memory. As I said, Win32F has 14 vocabularies. These segment the words by their use. So of course, we'd realize that when you're editing, you're only going to be looking at and utilizing the words that are in the editor. Same with the assembler and so on. A key element on vocabularies is that they facilitate the compiler search. Win32F has roughly 6,000 words in it. You wouldn't want to search all those words at any given time, so you can restrict the search to a shorter number of words, such as Fourth, as I said. And finally, vocabularies assist in recalling words. If I am working in, say, the assembler vocabulary, I only really have to focus on and remember the words in that particular vocabulary, and the sets of words then would support that one application, that one purpose. And finally, there's always a preference within modern programming to suppress detail, to suppress unnecessary detail, and so it's certainly done within Win32F. There's a vocabulary called hash. Well, hash has some 600 words in it, but they're words that you would never use in applications. They handle the keystrokes on the keyboard coming in and on bit banging and line drawing on the screen. So they are put into hash vocabulary, and it's unlikely you're ever going to use them. So what is a vocabulary? Well, it is a linked list of words, which is located in the dictionary and identified by name. So when you use that name of that word, you are now calling into use the list of words that is represented by that name. Word searches take place by the name in a vocabulary, and the way that this is done follows a specific syntax, which you'll go into. So when I want editor words, I can add the word editor into the search order, and then the searching will be done just within that particular set of words. And the syntax specifies the vocabulary into which new words will be added. As we'll see, there is one group of words which are called the context, which is the words in which are examined, and then there is a specification for current, and that current vocabulary is the vocabulary in which words will be added. Here's a trip down memory lane. If we look at Fourth from the 1960s, when created by Chuck, into 1982, the Fourth was a tree structure. Fourth itself, the blue line in the middle, contains the core words for the entire system. Somewhere along the way, though, an assembler set of words is added, and then editor words are added, and then finally you can add application words. This linkage is done at the time when a vocabulary is named. So the assembler vocabulary is created when only a small number of words exist in the system. Generally, this little called core or nucleus words. When a search is made at the assembler level, it only can search down all the length of the red line and then the little short stub of fourth at the bottom. Using editor gives you access to more of the fourth words. The application does more than that. This would be a search in that time frame. The context specifies a vocabulary that will be searched. So in this case, it points to application. A word search will go down all the application list. It joins the fourth and continues down to the bottom of the blue line, searching all of fourth. However, words that have been added to the system above the joining of that yellow line will not be searched. A second search pattern is set up by the word current, because current, and it specifies the point at which words will be added. So in this case, new words will be added at the top of the fourth vocabulary. And if I remember right, the older search pattern actually looked for both search the context and the current vocabulary. So you had two ways to set up your search order, and that was it. Remember, current for additions, context for searches. So the limitations, well, first is that the vocabularies are linked at the time of creation. You can't change that linkage. And forgetting can have side effects across vocabularies. We see in that tree structure, if you were to do a forget at one of the lower levels of the tree structure, you are now interfering with what could be the searches that are done. So forgetting had to be done with a conscientious worry about keeping the integrity of vocabularies. Also, I found that if you have an application that has more than about 5 vocabularies, you're going to get into some trouble on searching, because you can generally only set up a search order that will search 1 or 2 vocabularies, and getting from one to the other can be a little bit difficult. And so in those days, if you're going to make a major change to the search order, a design change, or a major functional change, it was common just to reboot the system. You reboot the system, bring up the editor, change the linkage points of the vocabularies, and take it from there. In 1982, I proposed only and also at the 1982 formal conference. As a bit of history, the formal conferences were done at Asilomar Conference Center near Monterey, California, and they ran from 1981, I believe 81, for about 18 years, up until the mid-1990s, early 1990s. They were a great event. They were 2 days following Thanksgiving, so we could have Thanksgiving on Thursday with our family, and then Friday and Saturday we'd have a formal conference, and we'd disband and leave on Sunday. So it was essentially a 2 full day conference. Great surroundings. It had proceedings that were published, so it was very professional in all aspects. So the result of only and also was that the vocabulary search order and the linkage between them is not determined at compile time. It can be determined at any time by words that specify the search order. Each vocabulary is independent. They are not interacting or interrelated. The fourth is a set of words with a beginning and an end, and the editor, assembler, and application are the same. Within Win32 the vocabularies are divided into sublists called threads. This is done to improve the search order or the search speed. If you have a vocabulary segmented into 11 threads, it means when a search is done, it will proceed 11 times faster than if there was only one thread. The cost of a thread is only 1 memory cell. In the context area, we have an array of memory cells that point to the vocabulary forming a search order. Each thread takes only 1 memory cell. The default in Win32 is 19. I'm not sure why 19 was picked, but it's a good, nice number. And again, as we'll see, it is prime and it is odd. If we wish to create a vocabulary with 19 threads, by default, we would just execute the word vocabulary followed by the text or the name for that word, in this case, a vocab. On the other hand, if we wanted to specify the number of three, we can do that by using the number sign vocabulary word. So 3 number sign vocabulary, B vocab gives us a vocabulary with only 3 threads. The thread quantity should be odd and preferably prime because a hashing algorithm is done on it, and this will ensure the greatest distribution of words across all the threads. The list of vocabulary, enter VOCS, voc. We'll see that 132.4 has 14 vocabularies. I've simplified the list down here, so some of them with little significance are omitted. The top level in green is 4th. It has 331 threads. We'll see why in a moment. It has 2,447 words, and that works out to 7 words per thread. If you're using the word dupe in an application, in a lot of fourths, you have to search through 2,447 words to find dupe. If you say dupe, dupe, dupe 3 times in a row, you've got to search that whole list 3 times. Within 132.4, there's only 7 words in the thread. So a word at the bottom of the entire order, you have to do 7 searches, but words in an application or near the top, you might only do 1 or 2 search. As a result, compile time in 132.4 is essentially instantaneous. I do large applications. Years ago, it would take, compile time might be 30 seconds to a minute. In 132.4, it's always a small fraction of 1 second. We'll see the vocabulary I mentioned earlier called hashed. It has 79 threads. This way, there's only 8 words per thread, and it has about 600 words. The assembler vocabulary has only 43 threads. As a result, the words per thread, as we see, are 16. However, the assembler is very lightly used, and so the fact it searches a little bit slower is not particularly important. Down at the bottom, we see the root. The root is a vocabulary, and it only has 3 words in it. We'll talk about that in a minute. And the locals vocabulary has 1 thread, and it has no words, because words are only added when locals are declared. So up until the time a local's been declared, there are no words in that vocabulary, and they are added upon use. So this is the search order that we'd see in a current system. The input declaration is only 4th, also editor, also application. The green pointer from context array points to a memory array area. And reading from the bottom up, the search order is now application because it's the last name, then editor, then 4th, and then root. At the bottom, we see application, editor, and 4th, and these are pointed to by the context array. So you start a search by going to the context array, you step down to the application, then the entire application is searched, and the same with other vocabularies. Notice they are independent, they are not linked. So vocabulary has a beginning and an end, and upon reaching the end, the execution goes back to the search order to find the next vocabulary. So how is the context array set up? Well, it's what I call a sticky array. It's not really a stack. It has some of the attributes of a stack, but it really is not a stack. The only word clears the array area. In the 132.4, this array can handle up to 31 vocabularies. So only clears the area and places root at the root of that particular list. And remember, now we'll see later, inside root, the only word of interest is the word 4th. So if we say only 4th, then 4th will then become the active vocabulary word. So when we execute the vocabulary name, the sticky part comes into place because the vocabulary name replaces the most recent context entry. Okay, it is not a push because it does not create space. It's more of a put because it puts its value into the search order on top of something that is already there. Only duplicates the most recent context entry. So if I say only 4th, Also, the also word has duplicated fourth, and now fourth is in the search order twice, but this is making room for the next vocabulary to be named. So we see the next step then is the word previous drops the most recent entry. So here's the differences between this and a stack. The only begins with a default value, also makes room for entries. The execution of a vocabulary name places entries, and then previous drops entries. And finally, the word definitions sets up another pointer which designates the word in which the vocabulary into which new definitions are going to be placed. The root vocabulary we've mentioned only contains 3 words: the set order, fourth word list, and fourth. Set order will load the search order from an array that it controls. So the set order is a way to initialize the search order. The fourth word list points to a list of vocabularies. All the vocabularies are in a linked list, so their access can be handled independently. And fourth word list points to that chain of vocabulary names. And fourth, of course, will place its value into the search order, and you now have a system that can actually function because it has access to the fourth vocabulary. Upon executing only, you'll only find those 3 words. Your only real choice is to execute the word fourth. And as we see, interpreting only is usually followed by fourth because you need that to complete further actions. The sequence we would have in this example is only fourth, also application, and then definitions, which means new words will be added into the application vocabulary. One of the magics of only and also is that you can place them into you can compile into a setup word. So I have the word here, :setup, and then the declaration only fourth, also applications definitions, which is exactly the same as would be interpreted above, but it's now in a colon definition. So anytime I want to get in that particular search configuration, I execute the word setup, and the rest is taken care of. There's another use for the ability to compile search order, and that is if you can seal an application so only the words in a specific list can be found. So if I execute only menu, only clears the stack, and you have to compile this. This will not work interpretively. So if you say execute setup, it will execute the word only, but the word menu has been already compiled. The vocabulary menu has been compiled. And so menu will become the top of the search order. And at that point, the system will only know the words in menu. So for example, if you were using this to control keyboard input, all of your text input from the keyboard would be located in the word menu. It's good to have an escape word. So if you have a sealed vocabulary, you need a way to get out of it. And of course, so otherwise you have to reboot the system. Now, actually, fourth is in the root. So you can get out of this of a sealed word list by using the word root. And we did an application for a chain of food stores. And to be able to do remote servicing on it, the store personnel only had access to a sealed vocabulary. But if you hit something like an escape ABX, this would break you out of the compiled program, get you back into fourth, and now you can do diagnostic work. A bit of a caution, the word previous can be hazardous to your health because when you make addition to the vocabulary, they are clear and they build up sequentially, but previous starts to disassemble the vocabulary of the search order, and there does allow some side effects and confusion. Imagine that you are interpreting a file, compiling an application, and you call another file by include, and that file executes the word previous. On returning to the main file, the search order is different, and you now have a major chance for error misinterpretation, and it may be difficult to find where that change has been made in a large application. So this is the reason I did not propose previous in my original proposal at Celeron in 1982. I felt that if you're going to diminish the search order, you should declare a new one by starting with only, or you should even better declare the search order as a word and then reuse that word. So rather than essentially breaking the search order, we would make a new one. Also, forget can produce uncertain results regarding search order. In a lot of systems, if you do a delete or a forget further down the search order chain, you can have a problem of destroying word linkages with catastrophic effect. I believe Win32 has what we call a smart forget, where when you forget a word in forth, it sequentially scans through all vocabularies, all word lists, taking the words away one at a time, kind of like disassembling a brick wall until it gets down to the desired forget point. So here's a solution for if you're going to make significant changes in the search order. The first principle is that a file should exit with the same search order that existed upon its entry. So if you are going to make changes within a search order, you want to restore what it was upon entry. So typically in an application or in a file, you may make some additions to the vocabulary, and then before you exit the vocabulary, then you would delete them back to the beginning value. Also, the adjustment by previous should only be used within a page or two in a single file. This means that if there's some confusion in the search order, you only have to look back a page or so to find out what it was, rather than trying to search through other files to find the side effect. And as I said before, the safest way is to compile the search order as a colon definition, execute that word, and you know what the search order is without ambiguity. And by using that process, you facilitated clarity and reuse. So as we saw in the Metacompiler situation, Metacompiler is often doing major vocabulary changes in between words, moving from one context to another. So here's an example that Win32 uses in metacompilation. Some of its vocabulary structures are at a situation called in forth. It has only forth definitions. In a context situation called in meta, it has forth, v image or virtual image, and also meta. And meta is the vocabulary in which new definitions are being built. And meta is the tool words that control the meta compilation. Finally, in transition is quite unusual. Forth is not contained. The only search order is forward, target, and transition. So at this point, you've created a new forth system and you want no access to the old one, because any words you would execute at this point would be from the old system, not the new system. So how can you preserve the search order? Well, there's a way. The word get order copies the entire search order to the data stack. In the case of forth, there are 331. I take it back. In the cases we've seen here, if you had 4 or 5 words in the search order, when you say get order, the structure of the context is copied to the stack. It may be 1 or 2 vocabularies. It could be 3 or 4 or 5 vocabularies, but that image of the context vocabulary is copied to the stack. You then can make some changes, additions, changes to the search order, and at the end of that sequence, if you execute search set order, the context area will be restored as it was at the beginning. So this is a very helpful way in which to use previous. You can get the order, make some changes. When you're all done, go to set order, changes are restored. So in summary on what we've seen here, when only and also were first presented, they caught it immediately. It was an aha moment. When people saw that, it eliminated the roadblock they'd had of having the fixed tree structure. It also was at the memorable 1982 formal conference at which Chuck revealed the magical create does. Up till this point, we were using Bill's does, and the structure was slightly inconsistent. The parameter field of a does word was inconsistent from all other words, and it was a kind of a little irritation, and you had to remember it when programming to make a couple of word adjustments. When Chuck verbally gave his presentation in about 4 sentences, the place went silence, and people murmured and said, "Whoa, what have we gotten here?" Because they could immediately see the value of what the new structure gave us. And finally, back to only and also, we see they are beneficial for large applications and for clarity. It improves the search order, and they are essential for metacompiling, because as we saw, metacompiling makes some very dramatic changes in vocabulary structure. So thank you very much. That's the end of my presentation today, and I will return back now to our fearless leader. Thank you.